So today I'm going to talk about a new algorithm for solving symmetric cone optimization problems. So if you don't know what a symmetric cone optimization problem is, let me just say straight away that it's a common generalization of linear programming, second order cone programming, and semidefinite programming. So while the title of this talk may seem esoteric, the actual topic is very practically relevant. Okay, so to just dive in and get it out of the way, let me define what I mean by a symmetric cone. So a symmetric cone is a convex cone that has additional algebraic structure. So in particular, it's the set of squares of an algebra J that satisfies the following properties. So first, the algebra J is commutative. Second, the multiplication operation is self-adjoint with respect to some underlying inner product. And finally, the multiplication operation satisfies a weakened form of associativity given by this second identity here. Okay, so examples of symmetric cones include the non-negative orthant, where the multiplication operation is just given by element-wise multiplication of two vectors. It also includes the cone of positive semidefinite matrices, where the multiplication operation is given by a symmetrized form of matrix multiplication. And finally, it includes the second order cone, where the multiplication operation is as indicated in the middle of the slide. Okay, so these are symmetric cones. The actual definition is not that important for the talk. The thing to keep in mind is that symmetric cones are cones of squares with respect to some multiplication operation, and also that there's an underlying inner product that induces a underlying quadratic norm. Okay, so those are symmetric cones. What is a symmetric cone optimization problem? So in this talk, a symmetric cone optimization problem has the following form. I'm minimizing a linear function subject to the constraints. My decision variable x is an element of my symmetric cone, and subject to the constraint that x also satisfies some additional linear equalities. Okay, so this generalizes linear programming, second order cone programming, and semi-definite programming. So if I plug in the non-negative orthant in for my cone, I get a standard form LP. If I plug in the second order cone, I get a standard form SOCP. And if I plug in the cone of positive semi-definite matrices, I get a standard form SDP. Okay, so in this general form, symmetric cone programs are well studied. So we have nice, elegant algorithms. We also have polynomial-time complexity bounds. And finally, we have software packages implementing these nice algorithms. So symmetric cone optimization has this trifecta of nice things. So we have elegant algorithms, we have theoretical efficiency, and we also have practical implementability. Okay, so how do these algorithms work? What is actually implemented in these software packages? So the most common algorithm for solving symmetric cone programs is the interior-poi method. So the way the interior-poi method works is we just track the central path associated with my symmetric cone optimization problem. So what is the central path? Well, it's the curve of solutions to the perturbed optimality conditions for my symmetric cone program. So the perturbation of the optimality conditions is being provided by this parameter mu, and it's being helped by the identity element of the algebra that underlies the cone. Okay, so if I plug in mu equals 0 here, these are precisely the KKT optimality conditions for the symmetric cone optimization problem. So if I have a solution to these conditions for mu equals 0, that means that x is optimal. So it solves my optimization problem. And it means that s and y are dual optimal. So these are optimal Lagrange multipliers, if you want, for my symmetric cone program. So I'll point out real quickly, you might expect s to be an element of the dual cone. Symmetric cones are self-dual. So that's why we're constraining s also to the cone k. Okay, so the big picture behind interior-poi methods, we initialize ourselves near some known point on the central path. We slowly reduce this perturbation parameter 0, tracking points on the central path using Newton's method, and we arrive at a point that's close to optimal. Okay, so what are some key theoretical properties of interior point methods? Well, we can bound the complexity it takes to move along the central path using the norm of the identity element and the log of the update to the perturbation parameter mu, or centering parameter mu, it's also called. So this says that the number of iterations it takes to move along the central path is bounded above by the log of the change in mu times the norm of the identity element. So for the case of linear programming, this is called the square root n bound, reflecting the fact that the norm of the all ones vector is the square root of n. For semi-definite programming, it's also called the square root n bound, reflecting the fact that the Frobenius norm of the identity matrix is the square root of n. So another important feature of interior point methods is an invariance property that they have. So if I start an interior point method on the central path, at each successive iteration I generate as I move along the central path, the affine constraints of my optimality conditions will be satisfied. So a way of saying that geometrically, the updates I apply to my decision variable x will always live in the kernel of this constraint operator A, and the updates I apply to the dual variable s will always live in the range of the adjoint of A. Okay, so this is the interior point method. So what is this talk about? So it's going to be a new interior point method that has a different invariance property. So instead of satisfying the affine constraints at every iteration, we're instead going to satisfy the perturbed complementary slackness condition at every iteration. And the way we're going to do that is by updating our decision variables x and s, not using subspaces associated with the constraint matrix A, but rather by using geodesic curves associated with the cone K. Okay, so I'll tell you this story in two parts. The first part, I'm just going to focus on the special case of linear programming. The reason being, the presented interior point method is going to have a completely elementary interpretation in this case. So it's essentially going to amount to applying a logarithmic change of variables to the central path conditions and then applying Newton's method. Okay, so I'll tell you that story. And then we'll generalize to the symmetric cone setting by essentially reinterpreting line segments in log space as geodesic curves of the cone K. Okay, so let's dive in and focus in on the special case of linear programming. So here my optimization problem is minimization of a linear function subject to linear inequalities and the constraint that my decision variable x is an element of the non-negative orthant, a symmetric cone. In other words, the decision variable x is element-wise non-negative. Okay, so to solve the linear program, what we're going to do is revisit our central path conditions, and we're going to rewrite them with the help of a log parameter v. Okay, so what's going on here is I'm representing x and s with their exponentiated logarithms. This gets rid of the non-negativity constraints. And then I use linearity of the complementary slackness condition in the log domain to reduce the number of log parameters from 2 to 1. So I represent both x and s, my non-negative vectors, using a single log parameter v, using the parameterization indicated by the system of equations denoted 2. Okay, so I've converted my central path conditions into a set of nonlinear equations in this parameter v and my dual variable y. So this suggests a meta algorithm for solving my linear program, which is to simply fix the centering parameter, apply Newton's method to these log domain central path conditions, decrease the centering parameter, and then repeat. Okay, so to my surprise, this seems unanalyzed in the literature in this precise form, which is kind of surprising given that it's a completely kind of elementary approach for solving the central path conditions. But nevertheless, I've been unable to find a reference analyzing these exact nonlinear equations. Okay, so let's dive in and analyze them. Okay, so Newton's method applied to these log domain central path conditions takes the following form. So all I do is I substitute in the first order Taylor series approximation of the exponential function into my central path conditions. And this gives me linear constraints on the update vector D, the Newton direction D. Okay, so I solve a linear system for this direction D, and then I update my log parameter V along this direction, perhaps scaling it by some step size. Okay, so what can we prove about this log domain Newton method applied to the central path conditions? So it globally converges if I use the following step size rule. So this step size says take a full Newton step unless the norm of the Newton direction meets a threshold, otherwise rescale by the norm squared. Okay, so if I start this Newton method at an arbitrary V and I use this step size, I will converge to some point on the central path, to the point on the central path corresponding to the given value of the centering parameter mu. Okay, so we can do more than establish global convergence. We can also talk about convergence rates. So if my log distance to the limit point, so my log distance to the central path is bounded above by this constant, then Newton's method will converge quadratically, which roughly speaking means that the accuracy will improve, will double with each Newton step. And here, this function is the inverse of the hyperbolic cosine function, which is providing me the constant defining my region of quadratic convergence. Okay, so how do I use this log space Newton's method to build a log space interior point method? Well, all I do is I just interleave Newton steps with decreases in the centering parameter. So the picture is I have the central path that I want to track. So I'm going to fix a value of mu, and I'm going to do Newton iterations until I converge to the central path. Then I'll decrease mu again and restart Newton's method until I converge again, repeating and repeating until the centering parameter mu reaches a threshold, and repeating until the norm of the Newton direction meets an error tolerance. Okay, so I haven't actually specified a rule for decreasing mu. So what can we say about different mu update rules? So the first thing I want to point out is if we just fix mu to a specified target value, so some mu perhaps really close to 0, this interior point method will globally converge from an arbitrary initial point V. The reason for that is that in this case, this is just implementing the log space Newton method that we analyzed on the previous slide, which I told you globally converges with the step size rule. Okay, of course we can do more than this. So there exists a way of updating mu that has the following complexity guarantee. So this mu update rule says that if I want to move from one point on the central path to another, the number of Newton steps, or rather the number of iterations I'll execute, is upper bounded by the log change in the centering parameter times the square root of n, where n is the number of linear inequalities I have in my linear program. Okay, so so in other words, this log space IPM meets the standard square root n bound for interior point methods. Okay, finally, we have an error guarantee. So when I terminate this algorithm, my log distance to the central path will be bounded above by epsilon, where epsilon is controlling the termination criteria as it pertains to the norm of the Newton direction. Okay, so this is a log space interior point method for solving linear programs. All right, so now I want to generalize this to the setting of symmetric cone optimization. So now my variable x is no longer a non-negative vector. It's an element of some specified symmetric cone. So how do we generalize our log space interior point method to this general setting of symmetric cone optimization? So the first thing we need to do is we need to reinterpret line segments in log space. So we're going to, in particular, reinterpret them as the minimizers of a particular arc length defined here on the slide. So this is measuring the length of a curve inside the non-negative orthant by weighting differential changes in the curve just by the inverse of the current value the curve is taking. So this multiplication operation is just indicating element-wise multiplication, and this inverse just denotes element-wise inversion. Okay, so the minimizers of this arc length, or the geodesics, if you will, are precisely exponentiated line segments in log space. So the shortest way to go from point A to point B with respect to this measure is to simply take a convex combination of the logs of the endpoints and exponentiate. Okay, so what else can we say about the geodesics of corresponding to this arc length? Well, we have a nice formula for the value of, for the arc length of geodesic. So a nice formula for geodesic distance. It's just the log distance of the endpoints. Okay, so the last important property to point out is that if I take a geodesic curve and I compute its multiplicative inverse element-wise, I get a new curve that's also a geodesic. So it's the geodesic connecting the multiplicative inverses of the original endpoints. And in terms of this logarithmic parameterization, this inverse curve just corresponds to multiplying everything in this exponent by -1. Okay, so line segments in log space are geodesics of the non-negative orthant. So to generalize this idea of geodesics to symmetric cones, we of course need to introduce a generalization of this arc length. So the generalization of this arc length is provided by a canonical map that identifies a point in the cone with a positive definite operator. So this mapping is called the quadratic representation. So I won't actually define it, but I'll just point out that it's a canonical object in the theory of symmetric cones. And if you like logarithmic barrier functions, it coincides exactly with the inverse Hessian of the log barrier function associated with the symmetric cone. So for that reason, this differential measure of arc length is sometimes called the barrier metric. Okay, nevertheless, I have a canonical measure of arc length for my symmetric cone. What can I say about the minimizers of this arc length? So what can I say about the geodesic curves? Well, it turns out that they also have a nice closed form parameterization. So geodesic curves are necessarily curves of the following form. So I take the quadratic representation associated with the starting point of the curve, or rather the square root of the starting point of the curve, and I apply it to the exponential map associated with the symmetric cone evaluated at some direction vector d times the argument t. So here, the exponential map is defined by our power series, and the powers of d are just computed using the multiplication operator associated with my symmetric cone. And here, the square root operation is also in reference to the multiplication operator associated with the cone. Okay, so this is an if and only if. If I can be written in this way, I'm a minimizer of this integral among all curves that share my endpoints. So another nice feature of this parameterization is I can just read off the value of this integral. So I can read off geodesic distance. It's just the norm of this direction vector d. Okay, so finally, this property of inversion also holds. So if I take the multiplicative inverse of a geodesic curve pointwise, I get another geodesic curve. And its canonical parameterization is obtained just by replacing w with w's inverse and by multiplying the direction d by -1. Okay, so this is all very abstract. Let's look at some concrete examples of this formula in action. So if I go back to the non-negative orthant, this formula reduces exactly back to line segments in log space. And it better because the whole goal of this slide was to generalize these geodesic curves that we've already seen for the non-negative orthant. Another example is the cone of positive semidefinite matrices. So for the cone of positive semidefinite matrices, this formula takes the following form. I'm going to apply a congruence transformation to the matrix exponential function evaluated at some direction matrix D. And this congruence transformation is just the square root of the starting point of my curve. So if I plug in t equals 0 here, this becomes the identity matrix, and I get that this evaluates to w. So g of 0 is w. Okay, so the geodesics of symmetric cones have a nice known parameterization. I should have mentioned up front that all of this is classical. You can read about it in textbooks. So none of this is new, but nevertheless, we're going to do something new with these parameterizations. So we're going to generalize our log splice IPM by using this nice formula for geodesic curves. Okay, so the way this is going to work, let me first just give you the template. The goal is to update a parameter w that encodes my primal variable x and my dual variable s using geodesic curves. So the things I need to do is I need to pick some value of the centering parameter, which fixes the correspondence between the parameter w and my actual decision variables. I also need to pick a direction, and I need to pick a step size. So once I've figured out how to do that, I can then update w along a geodesic curve and then just repeat this procedure. Okay, so properties I want to highlight of this geodesic update. So this is actually equivalent to updating the inverse using this formula. So this template algorithm is in no way actually giving preference to the parameter w and hence the variable x. It's symmetric with respect to x and s, because again, this update is equivalent to this inverse update. The other thing I want to reemphasize, this update is something that we compute. So for linear programming, it corresponds to just taking a step in log space. And for semidefinite programming, it corresponds to evaluating the matrix exponential and applying a congruence transformation. Okay. All right, so what do I need to do to turn this into a real algorithm? Well, I need to give you a recipe for computing a direction d. Okay, so the direction d is going to come from a geodesic version of Newton's method. So all we're going to do is we're going to take our geodesic update formula, we're going to linearize it, and then we're going to substitute it back into our central path conditions. So this gives us a nice linear system where my variables are this dual parameter y and my Newton direction d. So what I'll do is I'll solve a linear system for d, and then I'll apply this geodesic update of my parameter w using some step size. Okay, so what can we say about this geodesic Newton's method? Well, we can prove that it globally converges to a point on the central path if I use the same step size rule we saw for the log space IPM. So the step size rule says take a full Newton step, a full geodesic update, if the norm of the Newton direction is less than a threshold, otherwise just rescale by the norm squared. Okay, so we have global convergence of this geodesic Newton method. What other properties can we establish? Well, we can establish local quadratic convergence. So if the geodesic distance of my current parameter to the central path is less than a constant, then Newton's method will converge quadratically. So we had the same condition for quadratic convergence for the log space IPM. We've just generalized it, replacing log distance with geodesic distance. Okay, so putting everything together, we get a geodesic IPM for solving symmetric cone programs. So I have a given symmetric cone program. I want to apply the interior point method idea, meaning I want to track the central path as I reduce mu to 0. So I have an algorithm that does this, that updates our decision variables using geodesic curves. Okay, so what exactly is this algorithm? Well, it's just the geodesic Newton method we had on the previous slide, where we've interleaved decreases in the centering parameter mu. Okay, so what can we prove about this? So this will finitely terminate if I just set mu to a desired target value, so a value close to 0. And the reason for this is for a fixed value of mu, this is just the geodesic Newton method we had on the previous slide. And I told you that it's globally convergent with the step size rule. Okay, so we can do more than this though. We can also bound the number of iterations this algorithm takes to move from some point on the central path to another. And the bound is just given by the log update of the centering parameter times the norm of the identity of the algebra that underlies the symmetric cone K. Okay, so this is exactly the square root n bound we had for linear programming. For semi-definite programming, it's also a square root n bound. And I should say that this algorithm for the case of linear programming is entirely equivalent to the log space IPM that we saw earlier at the first part of the talk. Okay, so I guess the final thing I should mention is, of course, we have an error guarantee. So this epsilon parameter that I'm using to monitor the size of my Newton direction, it ultimately controls the geodesic distance of my decision variables to the central path when I terminate. So the geodesic distance at termination will be bounded above by epsilon. Okay. So with that, I'm going to start wrapping up. But first, I'm going to briefly advertise a software package that implements this interior point method. So this is still under active development. But what is the goal of the project? So the goal of the project is to support optimization over arbitrary symmetric cones. So this is a new solver for linear programming, second order cone programming, and semidefinite programming. For fun, we also support the more esoteric symmetric cones. So the symmetric cones that are defined by PSD matrices consisting of complex and quaternion entries. And finally, we support the so-called exceptional cone, which is defined by Hermitian matrices that have order 3, whose entries are octonions. Okay, so the goal of this software package is to be competitive with the state of the art. So for that reason, we have fancy sparse linear algebra routines. We have approximation methods for the matrix exponential, which is important for semi-definite programming. We also have fancy algorithms for computing eigenvalues. So just a teaser of computational results. So here's a comparison of our implementation of the log space interior point method to a widely used solver, STP-T3. And what this sea of numbers is indicating is that our solver is just as accurate and quite a bit faster. So much faster when the number of equality constraints for these random SDPs is small compared to the order of the matrices. So that's what we see by comparing these columns up here. So this speed up advantage diminishes as the number of equality constraints increases. And the reason for that is both solvers are essentially doing the same amount of work solving for their Newton direction. Okay, so I'll talk more about this in the software demo on Thursday. So let me end then on just a conclusion slide. So in summary, I presented a new interior point method for symmetric cone programming. For linear programming, this reduces to central path tracking in the log domain. I established that the complexity of this algorithm meets the state of the art. And I also just briefly advertised a software package, Connix, which implements this algorithm. So you can find a preprint of this on my website, and you can find the still under development software package at my GitHub website. So with that, I will thank you very much for your attention and answer any questions that you might have. Thank you very much.
Great. Thank you for a very interesting talk. We have a couple of questions in the chat, so maybe Henry, do you want to ask your question directly?
Sure. Hi, Frank. Thanks for the talk. I'm not sure if it's really a relevant question, but there was an old approach to SDP called the Q method. This was by Alzada and his student Yu Jia. So they parameterized the, if I remember right, the SDP constraint using the exponential. So e to the minus is. So I guess it's a different parameterization because you're trying to parameterize non-negativity while you're doing complementary slackness.
Yeah, so if we're thinking of the same paper, my understanding is they're using the matrix exponential to parameterize orthogonal transformations. So it's a technique for, I guess, like rotating the semi-definite cone.
Right.
Yeah, I'm aware of that paper, but it is a distinct approach to what we're doing.
Nima, do you want to ask your question too?
Yes. Do you hear me?
Yep.
Yes.
Yes. Thanks for the nice talk. I just had a quick question. How do you find the geodesics, by the way, from the formula that you used in your algorithm? Uh, how can we find them? How can we find the exact formula for the geodesics? And again, how can we show that they minimize the distance between, for example, two arbitrary points?
Sure. So let me maybe bring my slides back up. Where did it go? Right. So we don't need to actually find geodesics. So that there's this magical property of symmetric cones in that we have an explicit formula for them. In other words, we have a parametric representation of geodesics. All we need to do is specify a starting point and then specify a direction. So I guess if perhaps you're asking the question, if I start with 2 points, how do I find this parameterization? There's formulas for doing this. It amounts to it's related to computing like matrix geometric means for the case of semidefinite programming. So for the case of semidefinite programming, if I start with 2 points and I want to construct this parameterization, that is, I want to construct D, this is just a linear algebra task. So did that answer the question, or?
Yes, I think so. I thought that you have an exact solution for geodesics.
I mean, like I can provide an explicit formula. If you hand me 2 points in the cone, we can hand you an explicit formula for the geodesic curve. It just amounts to constructing the right direction vector D, but there's an explicit formula for it.
Okay. Thank you.
Frank, one question. So you didn't say much about the initial point. So somehow in here, this is a feasible method. So you're assuming that if you look at the equations that you were,
yep.
Those equations, right?
Yeah. So somehow, the central path conditions.
Yeah. So somehow I have to that requires a x equals to b with x positive semidefinite to be feasible.
Yeah. So I swept it under the rug, but underlying this whole talk is we assume existence of the central path, so a Slater condition for the primal and the dual. So under that condition, the global convergence theorem still holds. I can start at an arbitrary point in the cone. It doesn't actually have to be feasible or anywhere close to the central path.
I see.
And this will still converge. But we still need the central path to exist. But that's the only assumption we make for global convergence.
So you would, so in general, you do a phase 1, phase 2, or do you do a self-dual embedding?
Yeah, so that's why the software package I'm working on is still under active development, because I'm still trying to find a good solution to this. So I've prototyped, of course, self-dual embedding, but I'm trying to get just a regular and feasible start method to work. But it requires kind of understanding the convergence, or I guess divergence behavior of the algorithm when the Slater assumption fails. So this is actually still something that I'm trying to sort out. But a backup plan is, of course, just to do use this technique called self-dual embedding, which moves an arbitrary cone program into a cone program that satisfies the strict feasibility assumptions.
Can I ask another question?
Sure.
So those two equations, what if you started with the original optimality conditions and did a linearization? Could you then parameterize after the linearization and get a similar Newton equation? So in other words, can you take the original optimality conditions and just say, I want to solve the original optimality conditions with a different parameterization? Because implementations of the original optimality conditions always require some sort of substitution technique anyway.
Yes. I mean, so I think in general, I mean, this sounds like knowing something a priori about the optimal phase or the optimal value. So I would say that in general, trying to explicitly parameterize the optimal faces is not going to be something I don't see how you would do it. But one thing you can do is you can just set mu equal to 1 e to the minus 15 and just do Newton from the start, trying to get a point near the optimal solution. So this can work well, but it can also work terribly, just depending on how bad your initialization point is.
And is this a predictor corrector type of approach?
No. So each Newton update that we're applying can just be interpreted as a corrector step for some value of mu. So there's no approximation of the tangent of the central path or anything like this. So it's an interesting direction. I haven't. I'm not sure how exactly it would work, but the way this algorithm works, every update we make is a corrector step for some value of mu.